Okay. Where did you lose it? Were you okay with number 6? Okay, so you lost me number 7. So you lost me on this one, right? Okay, let's do it again. So, what am I talking about? So, let's say I had something happen at 12:50 p.m. Something changed, and my delay is 7 minutes. Okay? So the input changed at 12:50 p.m. That's what my input is. Okay? The output is not going to start changing until 12:50 plus 7 minutes of the delay. So the output will only start changing at 12:57. So y prime will stay 0, and carefully, that's y prime, not y not prime, okay? Stay 0 until, of course, 12:50, but also until 12:57. All right? And let's say I found out that I don't have a corner, no input response, and I have oscillations that I see, observable oscillations, so I have something like that. Eventually I'll reach steady state. And we'll talk about the definition of steady state in a minute. So, visually speaking, let's say I'm steady state about it. Okay? I'm telling you the time at which I have reached steady state. So T, steady state. That's what I'm talking about. At what time I will have leveled off. Clear? With me? So, I'll be able, with a very simple equation, tell you how long it will take for me to reach this state. We're doing all that without having to invert. In your homework, the very last problem, you have to invert and do partial fractions, expansion, and everything. You understand? Right?
Yeah.
So in the homework, I want you to do everything qualitative, and then do the work with the quantitative and see how close and how well the qualitative you all did compared to the actual quantitative response. That's the point of your homework. Okay? And it was kind of a review homework that did everything from the beginning. All right. So you understand? That's what I'm talking about. What is this time? So this time will obviously be the beginning time, which is T naught plus D. This is T naught. This is T naught plus D. Okay? So, and I'm saying the extra time from T naught plus D until steady state is going to be 4 tau dot. Okay, why? So, Shana, okay so far? So, what we would have is that y prime will be 0 for t less than t naught plus d. And then I will have a partial fractions expansion, and because of the delay, the time the step change happened, instead of having e to the minus pt, remember h of t is replaced by h of t minus d. If I have a step change happening at t naught, h of t would be replaced by h of t minus t naught plus d. So your h of t would have been something e to the minus p1t plus something e to the minus p2t and so on. Let's say my p's were, let's say, minus 2, minus 5, minus 8. Well, that's not minus 1, so that they're not in. This guy contributes something e to the minus 2t, actually e to the minus 2, instead of t, t minus t naught plus d. That's what this guy contributes. This guy contributes e to the minus 5. Same thing. Each of the poles contributes an e to the something, right? 3.
So that the something that's in front of the e, those are the C1s that we're going to
Yeah. Yeah, exactly. Those are the C's. Now, let me ask you something. When does my system reach steady state? When I stop changing with respect to time. All the poles to the left of the dominant one, here would be the dominant. That's the right. Okay, the rightmost is the dominant. So that's P dominant. In this case, -2 is the dominant pole. Dominant is whichever is the rightmost. With me? So all the poles, Robert next right there, okay? All the poles to the left of that pole have a higher number -e. So those guys die out a lot faster than this guy. This goes to 0 a long time before this goes to 0. When do I reach steady state? When all those exponentials disappear. That's when I have steady state. The last exponential to disappear is the one of the rightmost one. But let me ask you a question. Tell me how long, mathematically speaking, will it take for a system to reach steady state? Infinity. Exactly. So in a sense, steady state is fiction, never actually happens, but practically speaking, yeah. Because e to the minus something t becomes exactly 0 only at the infinity. So the actual steady state will never happen. But practically speaking, we're operating steady state all the time. Because if it's small enough that we don't see the changes, if the change of the system is fifth significant figure, it looks flat line in our instrument. If it looks flat line in our instrument, we are steady state, darn it. Even if it looks a little bit around, noise around it, we say it's steady state, right? Because never it will be flat line, that would be noise around. So if the trend has disappeared, if the trend is constant, we say steady state, right? So I will reach steady state when I can no longer see the e to the minus something till the dominant. Now, when does something disappear? At time 0, it's e to the 0. So here is time, here is e to the minus, let's say, 2t. At time 0, this is 1. But actually, let me write it e to the minus pt. Sorry, let me do it a bit better. Tau dominant is -1 over the real part, and remember, if I have complex, I will have, if I have something like -10 plus or minus 5i, what will I get? I'll get e to the minus 10t cosine and sine of 5t. So the real part will be in the exponent. The imaginary part will be in the cosine or the sine. Okay? So, the real part, another way you can say that is the real part, P dominant, is going to be -1 over the way I define tau dominant. So I can rewrite this part as, I can rewrite e to the minus pt as e to the, and remember p is negative, otherwise I will be stable. So this will become e to the, okay, so, oh, sorry, e to the plus. Yeah, it's e to the plus pt. Sorry, I missed that. E to the plus pt is what I get. Okay, the p is -5, it's e to the plus pt. So e to the pt can be rewritten as e to the minus t, okay, over tau dominant. I messed it up. So let me do it again clearly. I don't have to look at your faces. I know I didn't explain that clearly. Yes, sometimes I know I have to start an explanation. Here we go. What we must have the surviving part, last term to disappear, will be e to the minus p dominant, everything else goes, it disappears much faster, t minus t naught plus the delay. That's the last term to disappear. Okay? Instead of having t minus d, if the step change happened at t naught, we have t minus t naught plus d.
Did you just do it again?
Yes,
Should it be plus?
I'm doing it better.
No, I'm saying it should be plus.
Oh! Yes, I just did it again, Bree, damn me. Thank you, Bree. Thank you, Bree. Okay, are we all with me? E to the pt, and that p dominant is a negative number. Okay?
So does that mean that those p's are positive?
Yes. Oh boy. Please correct, change that to p. Oh yes. Clearly, I'm not making a joke with you, sorry. Make the correction. Please change those to p. Anything else I forgot? Yeah, the p's are negative, it's with the plus pt, which is e to the negative something. Okay? So let's do it right. So this is the last part to disappear. Okay? But tau dominant is defined as -1 over the real part of the dominant pole, which means that the real part of the dominant pole is -1 over tau dominant. So this is the same as e to the minus t minus tau naught plus d divided by tau dominant. With me? So let's look at what this thing looks like at different times. So here is time, and here is what this part is. So at the time a system starts moving, tau t naught plus d. What is this part? 1, right? At t equals t naught plus d, you have e to the 0 over tau dominant, e to the 0 is 1. So that's what we have the moment the change happens. And this thing continues towards 0 as time goes to infinity. What would happen, what is it equal to if I go 1 tau dominant after that? What would that be? If you put t equals t naught plus d plus tau dominant minus that over tau dominant, you get e to the minus 1. Which is about 0.37. So that term starts at 1, and after 1 tau dominant, after the system starts moving, it will have dropped towards 0.37. Ends up finally where? As time goes to infinity, what happens to this guy? As time goes to infinity, where does it go?
0.
It goes to 0. So this is the term at steady state. When this guy is 0, this is the last term to die out, we are definitely at steady state. When we are practically 0, we are at steady state, into practical steady state. So ultimately we're going to put, after, so at time 0 it's 1, here's time 0 and it's 1. At time 1 tau dominant, past it, d naught plus d plus 1 tau dominant, it has fallen to 0.37. That means I have moved 63% of the distance towards the new steady state. Okay? Only 37% is left. I have moved 63% of the distance towards the new steady state. After 2 tau dominants, someone with a calculator, I don't remember exactly, e to the minus 2, it's about 0.15, 0.14 something.
Wouldn't that be 1?
Yeah.
And 0 is?
Oh yeah.
Yeah, that's why we're sitting.
Oh, I am not doing well today.
today.
That should be 1, yes. I did it correct on the graph. Yeah, it should be 1. E to the 0 is 1. I said 1. I put 1 on the graph. I always see it. So e to the minus 2, is it about 0.14, some 0.15? 0.14, so 0.86, 0.14. So, okay, so we moved 86% towards the new steady state. At 3 tau dominants, we would get e to the minus 3. That's about 0.05. Right? Now we have moved 95%. So after 3 tau dominants, we're down to 0.05. So 2 tau dominants were 0.14, 3 tau dominants were 0.05. Some people consider that the time to reach steady state. Remember, the real time to reach steady state is infinity. So let's say if you have traveled 95% of the distance, you're close enough, you're within the noise, that's time to steady state. Most people, though, go 1 time constant further. If you go tau naught plus d plus 4 tau dominant, you get e to the minus 4, which is about 0.02. Sorry for that. Now you have traveled 98%. You have 2% of the origin. That looks flat from that point on.
In MED, we did 5 time constants.
Huh?
I think we did 5 in MED.
Yeah.
Energy balance.
You did 5? You did that in anything? Very nice.
With time constants, we dealt with some time constants, and we said 5.
It's like the 5 flush rule.
5 flush rule.
Yeah, something like that.
For control, it's normal to have 4, consider 4. I guess 5 would be 99%. So I'm using 4 guys in this class. Okay? You understand the rationale now behind it? So we can completely say time to reach steady state as what I wrote up there, T naught plus D plus 4 tau. So we can say all that without actually solving for the system and doing all the inverses, etc. Which you will do for comparison in your homework. Hope you have already done. So let me go to your homework and do an example very, very similar. I'll just change the number maybe. Your homework. Okay, I will do the screen that one to use. Let me load up your homework statements. It's only fair. Since you only have very little time, it's only fair that I try to do the homework. The part that you couldn't do last week.
Yes.